Page 120 and 121. 44. So I have this piecewise as defined before 44, right under 43. I hate the layout of this book. What? The solutions? Everybody always asks about the ones like that because of the way they... So you don't need it or you do need it, Joyce? Okay. Does anybody need 44?
I got B. Is B the answer?
Yes. Didn't do it. 44 is B. It's the left-hand derivative, so you would use this, and you should get 2. Number 7.
I got it. I put you to go over it again. And then do number 6 too.
Okay.
6 and 42. What's that?
I don't think you need to.
Is that not A? Answer A is what answer.
Did you just put A?
Yeah.
You're supposed to graph the
Is it differentiable on its whole domain?
differentiable?
Yes, why?
It's not a constant.
There's no cusp, corner, vertical tangent, or discontinuity, so it's differentiable. It means that you could take the slope of the tan line at any point on that curve. It exists.
It doesn't have the same slope on both sides.
That's not differentiable. So if you had like this absolute value like this is continuous but not differentiable at this point. It's continuous, the limits are the same as I approach from both sides. And the function defined here is that, right? I can draw it without lifting my pencil, but it's not differentiable at that point.
Or A is like 2.
What? Y'all.
You had to answer A, B, and
Is it differentiable? Yes or no? Yes.
I put A.
It could be.
No. At what domain point does it appear to be?
So you have to do all of
Should be all.
So that's over its whole domain, right? So part A, where is it differentiable on its whole domain? So -2 to 3.
And then the rest are just none.
Continuous but not differentiable is none because it's always continuous, but it's also always differentiable. Look, you answer A, B, and C. You answer each one of them. You give the places where that happens. Where is the function differentiable? On the interval -2 to 3. Describes the entire, right. I could see you thinking that, yeah. It's kind of confusing. Where is this function continuous but not differentiable? Nowhere, because it's always continuous and it's always differentiable. The absolute value, that's a perfect example. Or a cusp like that. That's continuous but not differentiable at this point right here.
So go back to so that's both.
Yes, that's both. Yes, that is both.
To get the slope.
Correct. The slopes all exist.
And what's the last one?
Neither continuous nor differentiable.
Is that just the slope?
Yeah, so if it did, so that's not continuous. It's not differentiable here. It's differentiable everywhere else, though. Just at one point is not right. Yes, yes.
Like, I know it's not.
Because the slope of the tan line coming in here, if it was A, this would be B. It would be different. Coming in here and here, the slopes are different. The left-hand derivative is not the same as the right-hand derivative at that point. That makes it not different. Right. If the derivative from the left equals the derivative from the right, then it is differentiable. If they don't, then it's not differentiable. That's correct. But the point they're getting at is it can be continuous but not differentiable. Okay, if it's not continuous, it's never going to be differentiable. That's one of the requirements of differentiability, is that it's continuous. So that's your, if you ever see it not continuous for any reason, you automatically know it's not going to be differentiable there. All right, so it is different slopes, but it's a gradual change of slopes. So they're both, remember we're talking about limits. So we're talking about as we get closer and closer to something, what is that value, right? And it's easing into 0 here. Whereas this is a constant slope coming in, right? The slope is always the same. Let's say -2. At this point, it literally just flips to 2 with no gradual anything. It is, but what, as I approach this, the slope is still the same as -2, right? But as I approach this one, it's getting closer and closer to 0. So like this slope might be -0.5, and then this slope might be -1/4, and then this slope might be -1/8, and it's getting closer and closer until it finally gets to 0. But this one, it's just -2, -2. Oh, all of a sudden it's not -2 and it's +2. This one is going to approach it from both sides, getting closer and closer. What else? Yes. 7. 7 looks like this, or something similar. So I would say, all right, is it differentiable? Well, where is it not differentiable if you say it's not differentiable? So it's not right, then it can't be, but that's the only place it's not continuous. So I would say if you put that it was neither, or if you put that it was differentiable, yeah, I would say neither for that, since that's what, yes, until we get a little bit further, yes, so that. Neither continuous nor differentiable. Because that's your problem issue, right? Your problem is at 0. And most of the time, if you've got a discontinuity, it's going to be just at one point. It's not going to be discontinuous over the whole thing. Yes. Okay, so 8's kind of the same thing, right? I've got this. Where are my discontinuities happening? Because I know that discontinuities x equals 0 discontinuity, which means it's not differentiable there, right? Because it's a discontinuity. And x equals, what is that? 2. It's what? Oh, yes. That's not a discontinuity. That's not differentiable because it's a corner. So if you think about it, instead of thinking about it, does it fit in A, B, or C, think about it like this. Where is the function differentiable? Where could you take everywhere but those 3 points, right? So from, what am I going from here? -2. -2, I can't include this, right? To -1. And then from -1, I can't include 0. And then I also, what is that one too? Can't include 2. And then from 2 to, what is that, 3? That's where it is differentiable. Then part B, where is it continuous but not differentiable? The only thing that's going to change here for part B, this is continuous. That point makes it continuous, but it's not differentiable. So I'm going to leave out for part B, I'm going to do all of this, but I'm not doing this part. Because this is 0. Because this is a corner. Corners are continuous, but they're not differentiable. So B asked me, where is it continuous but not differentiable? So this is all continuous until I hit 0. 0 is not continuous, and then it keeps going until I hit 2. 2 is not, you see the difference? And then part C is even different because it says where on this graph is it neither continuous nor differentiable. So it's neither one. At x equals 0 and x equals 2. Does that make sense? For sure. See the difference in continuity and differentiability, because that was the point of it. Did you see the difference in those two? You would need to graph this on your calculator and look at it. So it's y equals the cube root of, it is a cusp.
They did it like algebraic.
I would not. I would graph that. Yes, I would definitely graph that. Yeah, this account. I would say that's a cusp, and that's why. I would graph it and look at it. If you graph that, what does it look like? It should take, if you think about what a cube root looks like, this is a cube root, right? The absolute value should just flip this one up. Is that what it does? So then it should look like this.
Okay, I have a question.
Is that what it looks like when you graph it? Yeah, what's your question?
When you first start out, like the things that are not people or whatever,
Mm-hmm.
that was first and
Okay, but it's the cube root of an absolute value, so it makes it a little bit different. So it's an embedded function. It's a composition of functions, which is why. So it kind of looks like these bird wings, which clues you in that there. It would have been a vertical tan there, yes, absolutely. Yes, ma'am. Yes. Yes. So that's a button on your calculator above tangent, second tan. Yeah. It should. It's going to have a discontinuity, but you got to tell what I'm thinking that it is a vertical asymptote there. But yeah, you can graph it and look at it. Corner. Vertical tangent. It's that cube root. All cube roots are vertical tangent. And since it's 3 minus the cube root of x, so this is just, if this is cube root, this one's been reflected and shifted up 3. So it's up here, and it does, nope. This is reflected, then it does this. So it's still the same thing, it's just been reflected and shifted up. So it's still a vertical tangent right there. What else? 43. Y'all been itching to get to 43. Cube root of x minus 1. It says, which of the following points is the derivative not equal to if you put it in your calculator to look. That's on your calculator. So essentially, I would look at each one of these. What's f prime of 1, f prime of -1, f prime of 2, and f prime of 0. And I'm going to assume one of them is going to give you an error when you do it. If I put, well, because you know it's got a vertical tan, right? It should have a vertical tangent at 1 because it's slid to the right one, right? So essentially, whenever I put this in my calculator, I should get an error message whenever I try to find the derivative here, which is happening at 1. So I would take out my calculator and I would put it in there, and I would say, okay, the third root of x minus 1 will come out, and I'm going to go math 8 y1 x, and I'm going to do it at 1. Ooh, I got a value. That's interesting. But I guess that's what it's saying is you have to know what that looks like and know that that's a vertical tangent, so that wouldn't be true. This is saying it's 100 whenever I do it on, what does y'all's calculator say? It does, when I put it on my calculator, when I do inderiv at 1, I did inderiv of that function at 1, I got 100. But it can't be 100 because this is a vertical tangent. Was that the limit? Yeah, same thing. Yeah. You should get an error. I don't know why mine's giving me a value. Maybe not.
What is it?
About 3 o'clock. This is when it gets fun. I don't know that anybody goes back and watches.
No, you can't even hear what people say.
You can't hear what we say.
Hear what I say. So I probably look like a dweeb because I'm like responding to these invisible conversations. Yeah. So and sometimes it sounds like I'm screaming most of the time, especially whenever I have to talk over. Like in third block, it's like I'm just screaming because they're so loud and I'm having to talk over them. But you can't hear them; you can only hear me because I'm right here by the mic. Much better. Did you talk to them?
Yeah, I just remember that you were getting them late.
They were better. They were better. Ready? Let's do one the long way just so I can prove to you that this works. I want you to find the derivative of x squared. Not at a specific point, but with just the formula. Using your difference quotient the way we've done. Limit as h goes to 0. Give me an equation for the general formula for the derivative of x squared. And you know by graphing, what should the derivative look like? It's a linear equation. That's exactly right. You want to erase? Yeah, so you can see what happens. I'm going to FOIL it out. So this is handy, right? Because if I said, what's the derivative at 3? Well, you could just plug into the f prime that's already there and say, oh, that's 6. What is the derivative at -2? Oh, well, right? 2x plus 0. I can't plug in a 0 for h until the 0 is out of the denominator. All right, so let me show you the shortcut here. This is called the power rule. This is the first one. The derivative with respect to x, and I say with respect to x because I'm sure you figured out by now, or I hope you haven't. If you haven't, that's okay. We'll be taking derivatives with respect to other variables very soon. But the derivative with respect to x of x to the some variable, right? To take that derivative, what I'm going to do, have y'all figured it out yet, by the way? You take the exponent that was there, right? It comes around front. So this would be n times x, and then you subtract 1 from it. So you take the exponent, this there, okay? It comes around front and multiplies as a coefficient, and then up here you subtract 1 from that exponent. So, right? So if f of x was, I don't know, x to the 8th, then what's the derivative? I didn't have to do a difference quotient. I didn't have to plug in that whole thing and do a limit. Yes, I did. But it is so good that you are grounded in that definition because it comes up so much. Don't forget it. Don't forget that limit is h goes to 0. All right, next one, derivative of a constant. Constant? Differentiability. We'll call it C for a constant. The derivative of a constant is always 0. I guess I should number these rules, but. The derivative of C with respect to x is 0. If this is a constant, C is a constant. Yeah. Can't find what? Are you sneezing? Stuffy. Let's keep going through these. What number rule is this? I don't know. It's 0. It's 0. The derivative of a constant is 0. You want an example? If f of x equals 5, then the derivative of f is... Oh, just wait. It's coming. If there's no variable on there. And that makes sense because think about what a derivative is. A derivative is the slope of the tan line. This is a horizontal line. What's always the slope of a horizontal line? There's no slope at 0. See how it all comes together? All right. Yep. I mean, she's talented. Do I like her? I wouldn't say that I'd be like, ooh, what's this pulling me on today? What, is it me? You sent a picture of me? Aww.
No, it's the other one.
You're good. If f of x is 5, then the derivative of that is just 0. The derivative of a constant is always 0. Constant multiple rule, I didn't mean to switch colors on you there, but I wasn't rewriting. Constant multiple rule, or y'all know this as a leading coefficient kind of thing. So if I have the derivative of some constant in front of some function, I'll call it f of x. Then to take the derivative of this, you can take that constant out front and then just do the derivative of f of x. It can just jump out front. So now that's, yeah, absolutely. So that's handy because what if f of x was constant multiple, which you know to be a leading coefficient, 2x to the third. If I asked you what's the derivative here of 2x to the third, well, I could say that's 2 times, and now I can just do the derivative of x cubed. Close.
Well, how are you just
What's the first rule that I told you about? This comes around front, so 3x squared, so it's 6x squared. Now you don't have to show all those intermediate steps there. I'm just showing you why it works, why that constant multiple rule works. Easy? Yeah. Sorry. I'm not falling for that. There are a total of 7 rules. They're easy. Actually, I don't do negative. I only do 6 of them. What number am I on? That's okay. Tell me when you're good. Constant multiple was what? 4? This was 4? Because nobody's ever done that to me before. It's very original. I wasn't real old, but I was, yes. Does anybody like their name?
You don't like your name? I don't think people like your name. But you look like it. What did I look like?
You don't like your neighbor?
Yes, I do. I love it. Sum and difference rule. This is going to be especially helpful as we find the derivative of polynomials. Keep him in line, Avery, because he's just... If I have 2 different functions here that I'm taking the derivative of, and I'm adding or subtracting them, I can split that up, and I can do the derivative of each one individually. So I could do the derivative of f of x, and then whatever I got in parentheses there, the plus or minus, the derivative of v of x. And what this really means I'll give you a second to catch up with me. As you're writing, if I start with a quadratic, we've already said that the derivative should be what? A linear function, right? So if I find the derivative of f of x here, I've got several different rules going on that I can use, right? I can do the power rule, I can split up, I can do the leading coefficient rule. So just looking at this, there's 7. There are actually 6. What do you think the derivative is? Because I can split it up. I can do the derivative of this, derivative of this, derivative of this. So what's the derivative of 3x squared?
Oh,
Agree or disagree? It multiplies and then subtract 1. Yes? Plus, what's the derivative of 5x?
that's the rough.
5.
Oh.
If you multiply, 1 times 5 is 5. And then if you subtract 1 from here, it's 0. And then the derivative of 2 is 0. So we're done. That one's 0, so you don't have to put, yeah. Not moving. Multiply by 1 and you get 5, right? And then 1 minus 1 is 0, x to the 0. Because the derivative of a constant is 0. I split them up. I saved the 2 hardest ones for last. I don't know that I have a favorite. I don't know. Yes. All right, these are the hardest. I'm going to give them to you and then we'll practice a couple. All right, this one and the quotient rule are the hardest. And they take practice and memorization, but I promise you it's easier than the difference quotient. To find the derivative, I do. So I'm multiplying 2 things together, right? And this doesn't necessarily have to be whole functions like this. I'll show you. All right, so I do the derivative of the first times the second plus the first, any guesses? Times the derivative of the second. You think? Wait till you get to some of these. So for instance, if f of x was, and we could FOIL this out and just have one polynomial, but instead we're going to use the difference product just as an example. Difference. The product property, Stacy, get it right. So do you see that I have 2 things here being multiplied together? All right, so the derivative would be derivative of the first. What's the derivative of that? 2x plus 0, so yeah, just 2x times the second. And you keep it the same. It's derivative of the first times the second plus, now keep the first the same, x squared plus 1 but take the derivative of the second. You could if it asked you to, depending on what they ask you for, you could. Unless they ask you for a simplified version, yes. We don't simplify unless we have to in here. No. And I realize we're going through these a little bit fast, not doing as much. I'm going to give you some easy ones to practice with tonight, and tomorrow we will probably spend the class practicing with these kind of problems. And some, yeah, I should just speak that we're going to be here because then that'll mean we're not. Okay, 6. Thank you, Robert. Yes. Tell me when you're good. Not you, bro. Button your shirt up. Did you just jump at me? Did you just jump at me? I embarrassed you? Did that embarrass you? You don't get embarrassed, do you?
I'm looking at me.
I'm not. You're causing a scene over there. Don't be rubbing on Mac's head or. Let's do quotient rule and be done. You're good. I'm only gonna do 6 because negative exponents still do the same thing. That's really silly to show you that because it's still the exponent property even if it's negative. It doesn't matter. This is the hardest though. If I want to take the derivative of one function divided by another function. I have to take the derivative of the top times the bottom, minus, and it has to be minus, the top times the derivative of the bottom, all over the bottom squared. The original bottom squared. Your book actually has the proof of all of these. I used to go through with calculus the proof of all of them, where we've used the difference quotient to put it in and we show that it works out. I didn't do that anymore because we'll just learn the rules. It is a waste of time. That's it. Let me do an example of this one though. F prime of x. So derivative here of f. Once you get in it's kind of, I don't know, I do a little sing song. I'm like, derivative of the top. Anyway, whatever. Okay, no. Derivative of the top, which would be what? 2x times the bottom minus the top times derivative of the bottom. What's derivative of the bottom? All over the bottom squared. That's yes. You don't have to yet. We'll get to some where you'll have to for various things, but